All right, continue with nuclear radiation. So let's talk a little bit about nuclear stability. So remember when we talked about stability, right? So all less than 83, right? So all less than 83 are stable, right? Greater than equal to 83 become unstable. But here's some of the things that, and these are not all the times, just some things that we can talk about. So if there are too many neutrons, remember adding neutrons makes atoms more stable, it makes the nucleus more stable, but too many neutrons makes them unstable as well. So they should have just the number of neutrons. If you look at like hydrogen, so I have H1, H2, and H3. So this has 0 neutrons. This has 1 neutron and 2 neutrons. And both these are radioactive. So too many neutrons makes it radioactive. Too few neutrons makes it radioactive. Because hydrogen, if you look at the periodic table, hydrogen's mass is 1.001, which says that this hydrogen is the most stable. Okay, so if you have too many neutrons, you could have beta emission. Remember beta emission? Right? And so if we have, remember our neutron, right, and this beta emission is the negative part of that neutron leaves, then what's left is essentially a proton, right? So high-speed electrons released are changing a neutron into a proton. So if you look at the top number above that E, right, the 0 says that I have a mass of 0, and I essentially are changing a neutron into a proton. Okay? If I have too many protons, neutrons, I could have, I could have beta emission or positron emission. So essentially, again, what I drew earlier, if I have my neutron, I have too many neutrons, then I can release this positive particle, right? And if I have that, then I have a negative charge on a neutron, which cancels out another proton, right? So essentially makes both of them into a neutron, right? So because this right here, right, if it's next to another proton, essentially makes that 1 neutron into 2 neutrons, right? So the atomic number decreases by 1 because it cancels out a proton. Right, so those are two things to think about, right? Nuclear stability, too many protons relative to neutrons. You could have electron capture, right? So if we looked at this down here, right? So electron capture, the reason why this is right, so 55 minus 1 is equal to 54. Right, the second one is incorrect because that 56 is not, 55 minus 1 is not 56. And this one, the last one is not correct because this is emission. So capture has to be in the reactant site. All right, so some uses for nuclear chemistry. Radiotracers are one. So radiotracers are radioactive nuclides that are introduced to organisms in food or drugs whose pathways can be traced. So we use them a lot in biotechnology to look at what proteins are doing with animals. So we'll make radioactive proteins and we'll study them. We'll make pieces of RNA with radioactive tracers to look at how that RNA is utilized and used. We use them in medicine. We do different scans of different parts of your body. We do to look for cancers, to look for renal function or how well your kidneys are working. We look at cardiac muscle and how well it's working. We do bone scans with radioactive tracers. So we do a lot in the field of biotechnology and medicine with radiotracers. If we look at this periodic table here, right? So our radiotracers are going to be things that are radioactive. If you look at right in the middle of the periodic table, you see this right here is technetium, right? And you'll notice that in all of these stable atoms, all the white atoms have stable isotopes. Technetium has no stable isotope. The reason is it decays so quickly it becomes something else. So we have to generate technetium that we use, and it changes to other atoms relatively quickly. So it's used in medicine a lot. If we look at some different radiotracers that we use a lot, we use iodine, right? We use that for thyroid and renal scans. Its half-life is 8 days. So what a half-life is, right? And we're going to talk about that in a minute. So a half-life is the time it takes for 1/2 of a sample to decay or change into something else. So if I had 1 gram of I-131 in 8 days, it'd be 0.5 grams left. In 8 more days, it would be 0.25 grams left, right? So each 8 days, half of it would transition into something else. We have iron. We use it for red blood cells because red blood cells have hemoglobin, which is an iron-containing compound. We have molybdenum. So the interesting thing about technetium is we have moly, right, with molybdenum that we use to make technetium, right? So metabolism, if you looked at technetium, which I showed you, we use it for heart, bones, liver, and lungs. So we use it for a whole bunch of stuff, right? But you notice all these half-lives are really short, right? Technetium is used, its half-life is 6 hours. So if I had 1 gram of that in 6 hours, I'd have half a gram, and then 6 hours later I had 0.25 grams, right? And it disappears really quickly. In 24 hours, there's almost nothing left. So we have other ones like strontium here, 2.8 hours. It's really, really short. Okay. All right. So half-life, right? Let's talk about half-life a little bit. So half-life of a radioisotope is the amount of time it takes 1/2 of a sample to undergo radioactive decay. Right. So there's some easy formulas. There's some long formulas and easy formulas. Right. So this one right here, right, is our formula we're going to use, okay? And let me expand it a little bit. So if we have our formula, M is original mass of the sample, right? 1/2 stands for half-life. And then X is T divided by T, right? So the capital T is elapsed time. And the lowercase t is time of half-life. All right, so if you look at our sample question down here, it's down here. The amount of H3 remaining after 36.9 years. The initial amount was 100 grams and the half-life was 12.3 years. So if you see, we look at it, right? So the 100 grams is the M, right? The number of half-lives, capital T, was 36.9 years, and the lowercase t is 12.3 years, right? So the elapsed time is the total time that's gone by, and the elapsed time is the time of the half-life, right? So if we plug that in, we get 3 here. And 1/2 to the third power is 1/8, right? Because it's 1/2 times 1/2 times 1/2. So if you multiply that, you get 12.5 grams. So in 3 half-lives, right, I get 12.5 grams. The first half-life, I get 50 grams. The second half-life, I get 25. And half of 25 for the third half-life is 12.5. I will give you more examples when I go over how to solve the homework. Because there's other equations that we want to bring in there as well, but I'll take some other time and do that another time. So fission versus fusion. Fission, we use fission reactions, right? So fission, we use that reaction to make energy. So it makes smaller molecules, or smaller elements, and we use that for atomic energy. So we use that in the production of nuclear power. So fusion, right, makes larger nuclei. So, and we find this in the center of stars. Right? So nuclear fusion is combining with small nucleons or nuclei to create more massive elements, right? Always involves a large release of energy, right? Commonly seen in the center of stars. So fusion, right? Seen in the center of stars. Fission involves splitting of a parent isotope into 2 smaller daughter isotopes, right? A nucleon is used to destabilize a nucleus, and that is associated with moderately large releases of energy, right? So fusion is huge releases of energy. It's much too big to be controlled in a lab. Fission creates a large amount of energy, but that's what we try to control for nuclear reactions. So if you look at a fission reaction here, and I'm going to have that fission reaction in a minute, right? So I get a neutron, right? That's a neutron. You notice that neutron, if I wrote it larger was this, right? It has a mass of 1, 0 charge. It's a neutron. It combines with uranium-235, right? It makes uranium-236, which is super unstable, and it splits, releases a bunch of energy and 3 more neutrons, right? So that's a fission reaction. Excuse me. Because my large nucleus made smaller ones. I get krypton and barium out of it, which are a lot smaller than the parent isotope. All right? But you'll notice that there's a little fusion reaction there. It's not classic fusion because I'm not making a nuclei that's larger, right? So there's microfusion that releases the energy that causes fission. So fission reactions, like I said, are used in the production of nuclear energy, right? 2 common fissionable isotopes, uranium-235 and plutonium-239. Now, plutonium is a lot more radioactive than uranium. So uranium-235 is, although it's radioactive, it's in that red, not purple, right? So it's moderately radioactive, but not super. But uranium is supposed to be 238. So 235 has too few neutrons, and it's unstable, right? It's a fissionable isotope because I'm able to get it started really quickly with a neutron. So it makes use of what's called a chain reaction. Sorry, I lost that word. A chain reaction to produce lots of energy. So again, if you look at the picture, I have uranium-235 right? And I get a neutron. Now I slow a neutron down, right? So I put my neutron through a moderator, and this moderator, right? So make sure you know it does. It slows. So we want this is going to produce a large amount of heat, right? Heat energy. So we want to make sure this reaction is slow. So we want to slow down the neutrons so not all of them have the energy that will start another reaction. Right? We only want a few of them to start the reaction, but not many. So we'll slow the neutrons down. So this neutron hits uranium-235, which is already unstable. It makes it uranium-236. And you'll see up here that 236 is very unstable, right? And that 236 will immediately break apart, right, and form 3 more neutrons. And those 3 neutrons, right, will put through some more moderation and have them find more uranium-235, which will make more fission reactions. Now, we'll also employ what are called control rods here, right? And these control rods here absorb neutrons. So part of what nuclear power plants do is they look at the temperature that the core is creating, where all these fission reactions are occurring. And if it gets too hot, they'll lower control rods in there. And the control rods are generally made of powdered graphite. They're big rods of powdered graphite, and they will absorb neutrons, right? So they essentially limit the amount of 235 that can react at one time. So remember, moderators slow down neutrons, and control rods absorb neutrons, right? And those are things that you need to know. So the 235, like I said, is hit with a neutron, it becomes 236. Fission of the nucleon fusion of the nucleon causes a release of energy. Fission reaction is initiated, and it produces 3 additional neutrons. So that's called a chain reaction. We won't go heavily into it, but that's how we produce nuclear energy. So nuclear energy, a small amount of isotope produces a tremendous amount of energy. So there's advantages to it. So there are currently 30 countries that have nuclear programs, right? Nuclear power steadily grew around the world from the 70s to the 90s. It's been declining since the 90s. Currently, the United States gives us about 20% of our electricity each year, right? And it costs nothing because we already have these nuclear isotopes, right? So nuclear power comes from a reactor where atoms are split to release energy. They don't use coal, fuel oil, or natural gas, so they don't add the greenhouse gases, right? But they boil water, and the steam from the water is used to produce electricity, and then it captures that to make electricity, right? So the problem or the question is, why is this bad, right? So it's not causing global warming. We already have the uranium that we're using. And I'll tell you, we're currently, it's the United States, we want to limit the countries who are not in those 30 from getting nuclear. So currently Iran and then North Korea are trying to up their production of nuclear energy. And the question is, why do all what are called G8 countries and G20 countries, these global communities of allies, why do they want to limit the amount of nuclear power these guys can produce? And the reason is the fuel rods that have all the uranium in them, right? The spent fuel rods, when they're harvested, they separate all the uranium out and they find all of the 235 that they can find, right? And that is fissionable isotope, and those are the isotopes that we can make nuclear bombs out of. So really, one of the purposes of nuclear energy way back in the 70s was to stockpile this weapons-grade uranium for future use. Now, the United States, we have as much as we could ever use. China has as much as it could ever use. Russia has as much as it could ever use. And now we want to limit these other countries from doing that as well, right? Because we've already been through the Cold War where We said, hey, you know what, if you fire a nuclear bomb at us, we'll just blow up your whole country. We got so many of them. But they're worried about some of these smaller countries that have agendas where they don't really care if they die as long as they kill all us with them, right? So I think that's really the fear of it right now. It's not so much the nuclear energy, it's what they can do with the nuclear products. So some disadvantages of nuclear energy. Disposal of nuclear waste is costly and difficult, right? So radioactive waste takes years to no longer be hazardous, right? So there was a 3 Mile Island. So this is an area in New York that had a nuclear meltdown. They said it released a little bit of nuclear radiation. It was not a huge, had a small meltdown, not a huge damage to the communities around it. If you look at Chernobyl, right, in Russia, Chernobyl happened, I don't know, well over 20 years ago, and there are still fires burning from the heat of that reactor. It's still so radioactive people can't go back, right? It caused hundreds of deaths. Thousands of people had radiation sickness, and it's still radioactive today, right? You look no farther than the Santa Susana Hills, right? Rocketdyne. So the interesting thing about Rocketdyne, it was hidden by the company that was in charge of it. That was Simi Valley, right? If you look up Rocketdyne nuclear disaster, they're calling that the single worst release of nuclear waste in our country's history. That's what they're calling it. It released, they said, roughly 450 times the amount of nuclear radiation that 3 Mile Island released. And that was right here in Simi Valley, right? We were still arguing up till about 10 years ago about who was going to clean it up, right? And I think the government finally passed a $38 billion bill, right, to try to clean that site up, right? The company who was bought out by Rocketdyne, who was running it, polluted our water, and that water was undrinkable, our groundwater, for 50 years, right? So waste needs to be stored safely without the potential exposure to ecosystem and people, right? Errors in moderation. Absorption may lead to catastrophic event, right? And like I said, 3 Mile Island, Chernobyl, and Rocketdyne. Those are 3 big examples, right? So nuclear reactors worldwide, North America, right? We have 118 reactors. We have 5 under construction. Western Europe, 115, 200. And then we keep going down. East Asia, Africa has 2. So we by far have the most. And we'll have to figure out if it's a good use. So we don't really, with all of the sustainable technologies coming out, I really don't see a need for it. Our nearest nuclear reactor is San Onofre, right? And I think they decommissioned that one just a couple of years ago. That's down towards San Diego. All right. Talk to you soon. Stay safe, stay well, keep your group small.